Okay, for topic three, we're going to talk about the basic graph of cosecant, and then we're going to look at a transformation graph, so a graph where we do some transformations of cosecant. Again, I'm not going to go too deep into secant and cosecant, but I want you to understand the basics. And the key to graphing cosecant is to actually graph sine first, okay? And then you can kind of sketch the rest of what cosecant is, okay? So for this graph, or for this section, we're going to be talking about y equals cosecant x, or f of x equals cosecant x. Remember that when we're graphing these trig functions, x is it's the x-axis. It's like the regular x-axis, and that's going to represent angle measures. And then y is going to be cosecant of that angle, so it's going to be a ratio. Okay? Now, when it comes to cosecant, we need to remember that cosecant is periodic like the other trig functions, and it has a period of 2 pi. Okay? We need to also remember that cosecant is the reciprocal of sine, and that's really important because if we can graph sine, which sine's not too hard to graph, we're okay at graphing sine. That one's not too bad. But if we can graph sine, we can easily sketch the rest of cosecant, and it's not too bad. Okay? Now, the domain of cosecant, we found this out back in 7.5. The domain of cosecant is all real numbers except integer multiples of pi. So remember, the way we can write that is, now that we're back to just the regular xy plane, we're going to say we're looking for values for x such that x is not equal. And the way we represent multiples of pi is we write pi times k, where k is just an integer. So that represents integer multiples of pi. So we would write this as k times pi, and then we tell our reader such that k is an element of the integers, okay? Now, because cosecant is the reciprocal of sine, we're always going to have issues where sine is equal to 0, okay? So domain restrictions occur when sine is equal to 0, okay? And basically what happens is when sine is equal to 0, we're going to get vertical asymptotes, okay? So it says when the sine function has an x-intercept, the cosecant function will have a vertical asymptote. Okay, so let's go to a separate document so I can show you just the basic graph. Like, I want to build the graph with you. I have a picture of it in your worksheet here, but I want to show you kind of how we build this graph. Okay, so let's go to this document here. Okay, so we're going to draw an x-axis, and we'll draw a y-axis. Okay. We'll say this is -1, this is -2, this is -1, this is, or +1, this is +2. And then let's say this is like, we'll say that's pi over 2. We'll say this is pi. This is 3 pi over 2. This is 2 pi. Okay, so let's say this is pi, 3 pi over 2. And then we'll do -pi over 2, -pi, -3 pi over 2, -2 pi. Okay, now we have to remember the 5 key points when we are dealing with sine. Okay, so the 5 key points, remember, are ends, center, and then quarters. So we know the period of sine is 2 pi. Okay, this is just 0. All right, so we're looking at this region from here to here. That's going to be one period of sine. And we want to split that region into 4 equal regions of the same size or the same like width. And then that creates 5 points. So the center is at pi. And then the quarters are halfway between 0 and the center. So 0, halfway between 0 and pi, and then halfway between pi and 2 pi. Okay? So we have important things that happen at those points. And what we remember, hopefully, about sine is that it goes through the origin. So that tells me the beginning is an x-intercept. So that tells me the ends, the beginning and end of the cycle of the period, and then the center, those are always going to be the same. And in this case, they're going to be x-intercepts. Okay? And then the quarters are going to be your max and your min. So we have a max here and a min here. And then we can kind of repeat that. So in this case, we would have a min here and a max here. So the graph of sine looks like this. And I'm going to do it as a dotted line very much on purpose because we're not actually graphing sine, we're graphing cosecant, okay? So generally speaking, if you're going to graph cosecant, start with just a sketch, like a dotted line sketch of sine, okay? Now we know that cosecant is the reciprocal of sine, so something really special happens. But we also know that when we have x-intercepts on sine, that tells me sine is 0 and cosine is undefined, okay? So we're going to have vertical asymptotes at all of these x-intercepts. So let's do those in red. So we're going to have vertical asymptotes at -2 pi, at pi, at 0 or -pi, 0, pi, and 2 pi. And then this is what the graph looks like. You have to remember that when we were talking in 7.5 about the range of cosecant, we found that the range of cosecant was really weird. It went from -infinity to -1, and then it went from 1 to infinity. Well, you're about to see why. So the max and min, they're going to be points that are shared between sine and cosine. So let's start with this, the first period that we drew. So we know this point right here is a point that's going to be shared between sine and cosecant. But what cosecant does is this. And then -1, the minimum, is going to be a point shared between sine and cosine. So this is what the graph of cosecant, or sine and cosecant, okay? So this is the graph of cosecant, okay? So hopefully that helps you understand that we have those weird things that end up happening at, whoops, I didn't mean to completely erase it. We have those weird things that happen at integer multiples of pi. Well, now we understand that we have vertical asymptotes at integer multiples of pi. You can see that now. And we also can understand that weird range where we had this like gap between -1 and 1, but otherwise we went off to infinity in both directions. So here you can understand how that works, okay? So let's go back to the original document and let's look at a transformation of cosecant, okay? Now, this is another situation. This is the graph of cosecant. I just wanted you to see it like drawn out. So this is another situation where for some lame brain reason, I didn't give myself a whole lot of room to work. Okay, so I apologize for that, but here we are. Okay, so if we have a situation where we need to graph y equals -2 cosecant of 2 pi over 3x, what we actually want to do is start with a sketch of y equals -2 sine of 2 pi over 3x. Okay, so we're going to graph this right here, replacing cosecant with sine just as a dotted line, and then we can fill in the curves for cosecant. Okay, so we need to address a couple of things. We know that we have an amplitude of the absolute value of -2, so we have an amplitude of 2. We also have a reflection. This negative right here means we reflect over the x-axis. Okay, so that's really important. We need to understand that. Okay, we also need to understand the period because we definitely have a horizontal stretch or compression because we know we have a coefficient of x. Okay, so we've got an omega right here. So this is omega. Okay, so we need to figure out the period of this new graph. So when we're dealing with sine, we have a period of 2 pi and we always divide it by omega. So we're going to take 2 pi and divide it by 2 pi over 3. So that's going to be 2 pi times 3 over 2 pi. So that tells me my period is 3. So that's cool because that's really easy to work with, okay? When you have an integer value for the period, it's always kind of like, yes, because it's not so hard to work with, okay? So we know that we have 5 key points, okay? So let's first look at our period, and we're going to split it into those 4 equal pieces, and then we can look at the 5 key points, okay? So now what is a bummer about this one is we have an odd number for our period, which makes it a teeny bit harder. Okay, so we're going to start by looking at the ends of the period. So they're going to be from 0 to 3, okay? So 0 to 3 are the ends of this period, so the beginning and the end. Slam jam in the middle of that, we have 1/2. So that's the center, okay? Now the issue is figuring out the quarters, okay? So if we're looking at quarter 1, we find the average of 0 and 1/2, okay? So 1/2 or 1.5 is 3 over 2. So we would basically take 0 plus 3 over 2 and divide it by 2, and that gives us 3/4. 3/4. So this right here is our first quarter, 3/4, okay? And then quarter two, what we do is we take 1.5 to 3. So we find the average of those two. So we're going to take 1.5, which is 3/2. We're going to add 3 to it, and then we're going to divide by 2, and we end up getting 9/4. So that ends up being right here. Okay, so those are our 5 key points. All right, now I know finding the quarters is a little bit hard. You just average the beginning and the center, and then you average the center and the end, and that gives you the quarters. Okay, so let's figure out our key points. We know that with sine, we're going to have intercepts, x-intercepts at the beginning, the center, and the end. So I always say ends and centers. So we know we're going to have x-intercepts here, here, and here. Okay, so we have x-intercepts there. And then we know the other 2 points. The quarters are where we're going to have our max and our min. Okay, now we have to be really careful here. So what we do is we look at, let's say, 3/4. So we know we're going to have some point 3/4. This is our first quarter. Okay, ordinarily on sine, the max is 1. So what we have to do is first multiply the max by the amplitude, or not by the amplitude, but by A. And then if we have a vertical shift, we add or subtract the vertical shift. Luckily, we don't have a vertical shift. So our quarter, at our first quarter, we're going to have a max or a min this time at 3/4 -2, because remember, we're reflecting our graph about the x-axis. Okay, so this is going to be right here. So that's our min. And then we had 9/4. Okay, so that would be our next point where we have a peak or a valley. In this case, it would have ordinarily been a valley. So we would have ordinarily had a min of -1, but we have to multiply that by A, which is -2, which now tells me I have a max at 9/4 2. Okay, so we're just going to sketch this. So we're going to do dot, 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 dot. And then we can keep this pattern going. So let's do a couple more periods of this, okay? So we're going to go here, here, here. We're going to have, let's see, an x-intercept here and here. And then let's see, we're going to have a max here, a min here, and a, not here, here, and a min here. So if we keep this going, we've got that. We've got another period. Let's do another period off to the right here. So again, let's see, we're going to have a quarter, a center, so an x-intercept, another quarter, and then an end. And so we'll have a min and we'll have a max. So when you're trying to draw cosecant, always start by just sketching sine. Even if you're dealing with transformations, just replace cosecant with sine and then sketch that. And then all you have to do is go in and fill in your vertical asymptotes and then your curves. So let's do our asymptotes. Remember, asymptotes occur at x-intercepts of sine. So we're going to have an asymptote here, 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 here. Gracious, I did a lot more than I thought, and then here. Okay, so in between those asymptotes, we're going to have those curves going up at the maxes and curves going down at the mins. So let's draw them. So we have this right here. Just know that you share that point. You share the minimum and the maximum point on the sine function. So make sure you understand how to graph sine and cosine, because we're going to do this again, but with cosine for secant. And if you can sketch the sine graph, you can draw cosecant. Okay, now technically that dotted line for sine shouldn't be there. I'm going to leave it so you can really see what's going on, but that is the graph of cosecant. That is very specifically the graph of y equals -2 cosecant 2 pi over 3 times x. Okay, so that's cosecant. Let's see. Last up, we've got secant, and then I think we're done with 7.7.